finding it with the page now.
Okay, so 4.3, 4.1, we didn't really do. 4.2 was the integrals, right? Well, 4.1 was integrals, 4.2 was summations. That's what it was. So we're going to do Riemann sums and definite integrals, and we're going to start learning what an integral really is. Not quite today, but as we go along. So you do not need to write this down. Please just observe and hang with me. Okay, so I have the equation of x squared. Square root of x, yes? And if I graph it from 0 to 1, this is what I would see. Now, we've talked about those left-hand sums and the right-hand sums when we did the summation formulas. Remember doing that? Overestimates, underestimates. Okay, but we don't want an over and an under. We want exactly what we have. Okay? Well, if we take these boxes, and are these boxes a consistent width? No. So they're not a consistent width. And what happens if I add more and more and more and more and more and more boxes?
They're going to get more drastically different.
Well, what do you mean by that?
Like the last, if you go farther, the last one will be like.
Oh no, but I'm talking about what I'm talking about is adding a box here, and a box here, and here, and here, and here, and here, and here, and here. And as I add more and more of these boxes, what's going to happen to my overage? Is that going to get smaller and smaller and smaller? Yeah. So if I can add infinite number of little rectangles, I should say rectangles instead of boxes, could I get almost exactly the area of that curve? Okay? The area in here. If I can do that. So what we have, what Riemann came up with is this Riemann sum. He says that if I take the limit as n approaches infinity, so that means the number of rectangles here, of the sum from 1 to n of f of c of I.
And ideas, please report to Mrs. McKinney's room. Devin ideas, please report to Mrs. McKinney's room.
Of c of I times delta x of I, and we'll learn what those are in a minute. If I do this, it's going to add infinitely many little rectangles, and if I add up all of their areas, I should get something that is pretty exact, because we know as things approach infinity, some things approach 0, correct? Okay, so what I have here is I've done the c. We will learn how to find c of I and delta x of I in a minute. But if I do that and I put it into the equation and I simplify the equation out, pull the constant out, find the sum. Remember we had formulas for I. The sum of I was n times n minus 1 over 2. Remember I had that? And then, so I squared was this. So if I use those to find the sum, simplify it out, and then find as n approaches 0. Well, as n approaches 0, I probably should simplify this. So I'd have 2/3. That would be, the n's would have completely reduced with the 4 and the 6, correct? And here I would have plus 1 half n minus 1 over 6n squared. Well, as n approaches 0, this is going to get infinitely large. And if I have 1 divided by a number that's infinitely large, is that pretty close to 0? We've talked about that with limits before, right? So that would be 0. And this would be 0. So the answer would be what? 2/3. Now, let's go back and think about this. We have this picture right here. Under here was what we had in the original picture right here. And if this area is 2/3, what's the area above it? 1/3, because it's from 1 to what? 1. So Riemann came up with this concept to find that area under the curve. Okay, area under the curve is used in statistical things. It's used in a lot of components of math. So we need to figure out how to use this. And so let's write some of it down. Don't write everything down. I want you to be specific about it. So we want a Riemann sum. Oh, I touched it. Okay, Riemann sums. You have to have f being defined, like it has to be defined on the interval of AB. So again, those are x values, remember? And let delta be a partition, of A to B by, this you don't need to write, like you need to know this right here. Write what I underlined. Do not write anything else of that yet. This partition of this, it just means you can partition it up. That's it. Got it? Don't overthink it. With width of delta, x sub I is the width, and I is subintervals. So this is the width of the rectangle. This is how many subintervals they are, but that's not that important. Okay? If C is any point in the ith subinterval of x sub I minus 1, x, the sum is. This is what the Riemann sum is. Right here. Okay? This right here is just domain. So what's the formula? I guess I shouldn't have. The formula is right here. See that? Okay, so it is the sum from I equals 1 to n of f of C sub I delta x sub I. I'm going to see something real quick. Okay. So this is the Riemann sum. Right here. Okay. That means you add up all the rectangles and you get the sum. You guys got that written down? Okay. So how we're going to use that is we're going to use it to evaluate. The whole goal is to evaluate a definite integral. So definite means it has a beginning and a end. It is not from here to infinity. The integrals that we were evaluating before, we were just finding the integral. We were just integrating. That was all we were doing. We weren't finding the area. We weren't finding anything else. So now we're going to move on from that. Now, if you look at this, again, it has to be defined on the closed interval of AB and the limit of the Riemann sum over the partition of blah, blah, blah. Okay, right here, the only thing that's changed, this is the Riemann sum. Do you see that? What has changed? I have the what of it now? The limit. And we will write it as the limit as x approaches infinity, not x, n, sorry. As n approaches infinity of the Riemann sum. No. Yes, should be n. I wrote x the whole time when I was doing my own notes. That's really not smart. Okay, this double bracket is just delta x. So, in front of this, write the integral. If you already wrote that, write that there. So, this is the integral from A to B of f of x d of x. Okay, so this, did you write this down? Okay, then, well, here. This is what you need to write down right here. Right there. Now, down at the bottom, we are going to, I told you I'd tell you how to find C sub I and X sub I, didn't I? This is X delta X, and this is C sub I. And I will tell you, you have to know what Riemann sums are, and you have to be able to do them, but you will not use them a lot. They're not practical to use. Take too long. Today, that's what you use. But in theory...
So are we going to use them in, like, future chapters?
You will need to know what a Riemann sum is, and it may be like, here's a Riemann sum, and you that way, but then you usually have another way to do it as well. Riemann sums can get very cumbersome.
What do you mean?
They can get very complex quickly, and you have to continue, and you'll see that today in our work. We have to do the limit as the limit of the sum, the limit as the sum, as you keep, like, you just have to keep carrying it down until you get to the point you can do it. So it just gets a little... I had to force myself to do Riemann sums today rather than another method. So it's not fun. Tomorrow you will appreciate what we learned. Okay, you guys got those 3 things down?
Yes.
Okay. So we need to evaluate the definite integral by the limit definition. That's what we need to do. So we need to go through this. We have the definite integral from -2 to 1 of 2x dx. Okay. If I graph 2x, it looks like this black line here, doesn't it? Right here. If I graph it? Yep. And I could just find the area, couldn't I? Because I have 2 nice triangles, don't I? But we have a problem. This top one would have a positive area, wouldn't it? What would this one come out?
A negative area.
It'd be a negative if you took into account that that's a negative, right? Like, because it's 1/2 base times height. Which we can't have negative areas, but we're still going to use the Riemann sum on it just to practice it. Okay, so in order to do the Riemann sum, which is the limit as n approaches infinity of the sum of f of c sub I and then delta x sub I. Yes? So we need to know what c sub I is and delta x.
Is that I on the delta x, like, lower?
It's a
Yes?
sub,
Okay.
yeah. It's really hard to make it nice and neat. So we need to figure out what c sub I is and what x sub I is so we can plug it in. So on the last slide, I told you that delta x was b minus a over n. Now, I guess I didn't talk about this, but this would be a down here, and this would be b. Did it have it on those definitions?
Yeah.
Okay, so you know, b is the lower limit, a is the upper limit. I guess I didn't point it out. I just kind of do it. Okay, so b is what, 1? Minus a -2, so b plus. And then n is n. So delta x is 3 over n. Okay? Make sense? So c sub I is a plus I delta x. Well, what's a? -2. Plus an i's I times, what's delta x?
3 over 9.
3 over n.
Oh.
So how I write it, guys, I just write 3 over n I. Because n is going to be a number, correct? So 3 over n is going to be a constant when we get there, isn't it? Okay. So if we ever theoretically get there, it would be a constant. So now we're going to plug these two things in to what we have. So we're going to have the integral negative 2, you already have this written, so you don't need to, of 2x dx is going to be equal to the limit as x approaches infinity of the sum from I equals 1 to n. I didn't write the indexes on there before, which I should have, of f of c sub I. So that means composition of functions, doesn't it? It means put c sub I into f. Well, what is f? It's 2x, isn't it? So c sub I replaces x. So it would be 2 times, and what's c sub I?
No. Negative 2 plus 3 over ni.
Negative 2 plus 3 over ni. And then it says times delta x sub I. Well, that is what? 3 over n. Okay, so now we are done with plugging it in. Now we have to simplify this.
Wait, I'm confused. The sub I, what does that do to it since it's just change of x?
Oh, this is probably, I should have put that. Delta x sub I.
That's not what it said on the first slide either, so.
It's fine.
Okay, it's sub I.
Yeah. Okay. So now we have to start simplifying. Well, 2 and 3 over n, is that not, that, like, that's going to be a constant, right? And don't we know we can pull constants out of summations, correct? Yes? So I'm just going to write limit. I am not going to keep writing as x approaches infinity. I'm not going to do it. It just gets too much. But I can take 3 times 2 is 6. So 6n, the sum. And do I need to keep writing 1 to n on the summation? Or can you guys follow that that's there? Can you follow that it's there?
Yeah.
Okay. And I have left, well, I took the 2 out and I took this out. So I now have negative 2 plus 3 over n I. Yes? So I need to remember my summation rules. Well, I know if I find the sum of a constant, wasn't it just from 1 to n? Wasn't it just the constant times n? I wrote a 1. Wasn't it? Wasn't that the rule? If I have the sum of 6 from 1 to 7, that means I'm adding 7 6 times, right? Or 6 7 times. So then I would just take 7 times 6. Right?
Yeah.
Okay. So this, when I do the summation for that, so I have the limit still of 6n, 6 over n. So I have negative 2n, because that would be the sum of negative 2. Now 3 over n is a constant, yes. So it stays here. Do you guys remember from the first slide, or do you remember before, the sum from I equals 1 to n of I was n and n minus 1 over 2, correct? That was the formula. Okay, so we have I here, don't we?
Yeah.
Okay, so we're going to put this in place. We're going to put the formula. So n times n minus 1 over 2. Okay, so we've taken care of the summation. Whew. Now we need to simplify again before we can take care of the limit. So we do need to distribute the 6 over n. Yes. But we also can do some can I reduce this n and this n? Yeah? So hopefully I'm not running out of room. The limit of 6 over n of negative 2n plus, now I need to distribute, see how I have 2/3 right here? Do you see that? Yes?
You need 3/2.
Did I say 2/3? I'm sorry, 3/2. So I have 3/2. So I need to distribute it into here, don't I? So that gives me 3/2 n minus 3/2. Okay. Now what do I need to do with this 6/n?
Distribute.
I need to distribute it again. So then I'd have when I distribute it to the -2, the n's reduce, correct?
Right.
And so I have -12. When I distribute it to the 3/2n, the n's reduce again. 2 goes into 6, how many times?
Right.
3. And 3 times 3 is
9.
9. So plus 9.
Wait, can you say how you got -12 again?
When I took 6/n times -2n,
Okay.
the n's reduced.
Okay.
Then -2 times 6. So now I have 6/n times -3/2. So it's going to be negative, right? 2's going to go to 6 how many times?
3.
3. But this time it's going to be 9/n because the n's aren't going to reduce.
Then wait, how'd you get 9?
Because which one? Just the plain 9?
Yeah, just plain.
Because the n's reduced.
Okay.
And 2 goes into 6 3 times.
Okay.
And then 3 times 3 is?
Wait. Hold on, wait a minute. Are you talking about both of the 3/2 that are up there?
Well, no, I'm only talking about this one right now.
So then wouldn't it just be 3/3, which would equal 1?
No. 6n times 3n/2. And it works on both of them, except on the last one, there's no n to reduce, so we have an n in the denominator. So now we need to add back in n approaches infinity. We're ready to do it. So, as n approaches infinity, what is -12 going to be? There's no n in there, is it?
No.
It's going to be -12. What's 9 going to be?
9.
9. But, remember, 9/n, this denominator is going to get arbitrarily huge, yes? And when I have 9 divided by 90 trillion, it's pretty much what?
Pretty much 0.
0. So minus 0. So the answer is what?
12. -12 plus 9.
Which is
-3.
-3. So the area of these regions are -3. Why is it negative?
Because the big ones.
Because the big one's negative. But can I have a negative? Can I have a negative area?
No.
No.
It's like negative stuff.
Right. So for this one, it would not do us any good to find area and say, yeah, the area is that's -3, because it's not. But we have this problem here. Is this continuous when it crosses like that? Is that a continuous function?
No.
What happens if I took this triangle and brought it up here and I said of these two areas? Is this a continuous function? What does it have right here? It has that sharp turn, right?
Yeah.
Right. So we performed Riemann sums and it did its job on there, but could we say that's the area for this? No, because it's not continuous. So what you have to make sure is you have a continuous partition to be able to do it.
So if we have one like that on the whole board.
Just do it, but know that it wouldn't count as area. Okay? So this one says evaluate the definite integral here. Okay, guys, 8. What kind of equation is that? That's y equals 8. Yes? What kind of a line is that? It's horizontal, right?
Yeah.
So it is horizontal. Like, if I were to graph this, this would be 8. I'm going to say this is 8, and it would look like what? That, right? And I'm going for what, 2 to 6? So 2 to 6. So what I would be looking at is only what?
That chunk.
That chunk. Is that continuous?
No. Yes.
No, I mean, is y equals 8 continuous?
Mm-hmm.
Yes. So this will work for us. So it says use the limit definition to evaluate this integral. So that's what we're going to do again. So the first thing we have to do is figure out delta x. Okay, well, delta x is what? What's the equation?
B minus A over N.
Okay, so b minus a, so 6 minus 2 over n. So it is 4 over n. Okay, and then I need c sub I.
Wait, so is a change of x still sub I?
Yeah, you're getting too hung up on your eyes. Just disregard it. Okay, so c sub I is a plus I delta x. So a is
The bottom 2.
2 plus delta x I. So the Riemann sum, let's see if I can remember it without looking, was this the limit of the sum of blah, 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 right? F of ci and delta x, right? Is that right? Please be yes.
Yep.
Okay. So we need to plug this in. So we have the limit as x approaches infinity of the sum from I equals 1 to n of. Now, this says plug C of I in everywhere there's an x. Is there an x? No, there is not an x, is there? So can I do this first part?
No.
I mean, I can't plug C as sub I in here. Even if I did, I'd still get just what? 8? Why would I just get 8? Look at,
There's no x.
there's no x. Here's my function right here. There's no x in it. So when I plug C sub I in, I still just get 8. Okay, so then I need delta x. What's delta x?
4 over N.
4 over n. So this one we're going to approach it a little bit different. Last time we brought like everything out. Well, we can. We brought this right here out, didn't we? Yes? But we also have this, don't we? So if we bring all of this out, we still have what number? Don't we still have 1? Because when I factor something out, I'm dividing, yes? I'd still have 1. But how many of us would forget to leave a 1? Me.
I would never.
You would never. I would forget to leave a 1. So when I have this situation occur, I have the limit. I only bring out my delta x. I leave the 8. So I don't forget that there's a 1 there. You can bring it all out, but you better leave a what? A 1. So then I have 4 over n, the sum of, how was it? Whatever. I to n of 8. Now, 8 is a constant, yes?
Yeah.
Okay, the rule for the sum of a constant is 8 times, what's your upper limit? N. So it's how many times between 1 and n? Well, that would be n, correct? So I'm going to have the limit of 4 over n times 8n.
Wait.
Because the summation rule for a constant,
Why would you add N to the 8?
because the summation rule of a constant is the constant times the number of things you're adding. Remember, that's... So 4 over n times 8n is what?
32.
Okay, so I have the limit as x, not x, and I wrote x earlier too. You guys need to catch me when I do that. because it doesn't work with x. N approaches infinity of 32, well, is just what? Is there any n's to manipulate?
No,
Nope, so the answer is?
still just 32.
The answer is 32. I got one more of these. Let me go on to something else. The textbook gave you the first one, and that was it. This is actually problem 3 and 4 in the homework.
Oh,
But you aren't assigned 3 and 4, so.
I was not ready to use her resources there.
Oh, you do?
yeah.
Oh, maybe this is 2 and I don't know.
It did say 3 on the
Oh,
one that we did.
well, evidently we're doing 3 and 4.
So we're
Unless I'm wrong. Okay, evaluate the definite integral from -2 to 3 of x dx. The first thing I do is what?
Find your limit. Well, no, actually, no. You have to find your change in x and your CI.
So your delta x, which will be 3 plus 2 over n. So 5n. And then c sub I, which will be
-2 plus 5 ni.
5 over ni.
Yeah.
I figured that's what you were doing. Okay, so then I have the limit as n approaches infinity of the sum from I equals 1 to n. You notice I put all of everything on the first step, and then as I go, I add it back in as I need it. So again, it's f of c sub I delta x, right? So we're going to put c sub I in for the x. Well, that's the only thing there, right? So it's going to be -2 plus 5 over n I times f of delta x, which is 5 over n. So we have the limit, and we're going to bring the delta x out because that is a constant, correct? So I have 5 over n, the sum, -2 plus 5 over n I. So I have the limit of 5 over n, and I have to use my summation rules again. What's your summation rule for a constant?
Multiply it by the
But-
upper limit.
Right, the upper limit, or how many there is, but we're starting at 1. So we're going to have parenthesis -2n plus 5 over n, and the formula for the sum of I.
N times n minus 1 over 2.
n minus 1 over 2. And now we just start simplifying, right? You guys want to try to simplify on your own?
Yes.
Okay. I will too, but I won't talk it out. I want to ask you questions.
What? Wait.
I'm just bad at like breaking it up. I got the -10.
So did I.
So-
That's it.
I was getting there.
So are you putting, like with 5/2 are you putting that in the denominator?
I'm doing this.
No, I know.
Oh,
Are you putting the in the denominator though? So that's how you don't get.
no, this n is in the numerator.
Then wouldn't there?
Because this n is in the numerator and this one's the denominator, so they reduce out. So I get 25/2. But in the next one, there's no n to reduce.
Which n? I'm so confused right now.
I have 5/n, 5.
No, I understand like how you. Oh my god. So then where did you get -2 in at? So then.
Okay, on the next one,
Yeah.
you have this. Which would be 2n.
No, I'm talking about -10. I'm not talking about like 25/2 or nothing like that.
Oh, well, the n's reduce, and -2 times 5.
Because it's -2.
Yeah, that's what I was asking. I was asking which n is where. Is -2n in the numerator, or is it?
Well, it's in the numerator. There's no fraction there. It's in the numerator.
Okay, so then 5/2n is in the denominator.
No, the n is still in the numerator.
So then how does that cancel out?
Because this one, right here.
This does not make any sense.
So when I find the limit, this all becomes what? 0?
Yeah.
And this should be -20/2. So I get 5/2.
Good work, guys.
So your homework